All right, good afternoon. Let's get started with today's lesson. So the first thing I'm going to do is I'm going to finish two examples I did not get to finish last time on exponential and logarithmic modeling. I think it's good to know those examples. They actually they're used a lot, and it's very close to our daily life, and you will definitely see them again if you take a, for example, a science class or engineering class, or even if I suppose for like I'm not sure which field you are going to focus on, but like if you take a health class, you might come across examples related to one of them. Or if you are into finance, at some point you probably come across logistics model, and so yeah, so they're actually used in quite a few places. And after that, we're going to talk about angles. So that kind of switch from exponential logarithmic function to trig function. So sine and cosine. We're going to talk about unit circle, and I'm pretty confident that you all heard the term unit circle before, but if you haven't, done trig for a while, you're probably not familiar with it. So that's my plan to cover them. But a quick reminder that we're going to have an exam on Monday, and that's going to cover everything from what we did last exam, I believe is 4.2, go all the way to 5.2, which I'm going to try to finish today. If that's anything remaining from 5.2 today I couldn't finish, I'm going to finish them tomorrow. All right, so that's a coverage for the exam. I would say don't freak out about the exam. Just try to think about it, maybe 2 or 3 quizzes combined. Just do your best, right? I know it could be stressful because they're exams, right? But just think about them as like a longer quizzes. I have to say though, the previous exam, I have not finished grading yet. I started, but I have not finished yet. But the quiz 3, which is related to the exam that we're going to have, that has been graded and uploaded to Canvas. So if you log into the website, you should be able to see the feedbacks and also your score. If there's any issues, feel free to email me. All right. Any questions? All right, then. If you don't have further questions, so I'm just going to get started with those 2 examples. The first one I have is called Newton's law of cooling or heating. They're really the same. So Newton's law of cooling, or sometimes heating. So there's a formula given for this type of problem, which is T of T is equal to AE to the RT plus TS. I'm going to explain what each term is. So what this law is applied to in the situation of, for example, we take something really hot, we're going to place in an environment of cold. So suppose this is, an environment has a temperature, and then we're going to take some hot object, put in there. This is some cool environment. And obviously the cool environment is going to affect the temperature of the hot object, right? So the temperature of the object will change. This could also be true if you have, let's say you take something cold and then you're going to put into some warm or hot environment. And then the cold object is also going to warm up in this case. So this formula applies for both situations. So that's why it's whether it's cooling or heating is really the same. It's just looking at how the temperature of the object change when it's being affected by the environment. And so this formula, I don't really expect that, well, you should know it when you see it, and at least know how to use it, right? I'm not going to quiz you on how to memorize it, but you should definitely try to know. So here we go. I'm going to explain the terms. So T of S is the temperature of the object. So that will change based on time. And then the A in this exponential part, so that's just going to be the initial difference between temperature of object and T and S, T sub S. Now, what is T sub S? This is the temperature of surrounding the environment. And the T sub S, again, so that just means temperature of surrounding. I just spelled temperature, right? My goodness, I can't spell at all. Temper. So temperature of surrounding. And we're going to assuming that the temperature of the surrounding is constant, it doesn't change, even if we put something hot in there, but because of the environment is so big, eventually that disturbance is being canceled throughout the environment. So the temperature of the environment doesn't change. So this is the constant. Now, so here we have an exponential decay or growth of the temperature. So here there's like an e to the RT. So the I, you can think about that like the temperature decaying rate or temperature rising rate. All right, does that kind of make sense? And then we're going to look at example on how to use it. So let me just copy this problem. So here's a problem I took from the book. I'm going to figure out how to copy it. But difficult. Oh, come on. There we go. So here's the example. It says a picture of, I know it's a bit small. Let me try to make it bigger. All right, give me a second. I need to. There we go. All right, here we go. That's better. So it says a pitcher of 40 of water at 40 degrees is being placed into a 70-degree room. So we can imagine, so this is the room, and a pitcher at 40 degrees is being put into the room that's 70 degrees Fahrenheit. And the 1 hour later, the temperature of the water in the pitcher is 45 degrees. And we want to know how long does it take for the water to reach 60 degrees. So because of the room has a temperature 70 degrees, so the water temperature is going to keep rising over time, right? We just want to know how long does it take to get to that point, 60 degrees. So this is the problem that we're going to apply Newton's law of cooling, because it's objects with a different temperature being put into an environment, and we want to know how the temperature changes. So we're just going to apply the formula directly. T of T, the temperature of the object, equals A e to the RT plus TS. And we can figure out the difference between the temperature of the water and the temperature of the room. So that's A equals 70 minus 40. The difference equals 30. And the TS is given, the temperature of the room, the surrounding. So that's a 70 degrees. And we don't know what R is. It's not given. And we do know that after 1 hour, so at time equals 1, the temperature of the object, T of 1, is equal to 45 degrees. So we can take this information. Let's take a couple of steps. The first step, I'm going to plug in the A and the TS. So I get T of T is equal to 30 e to the RT plus 70. And we still don't know the rate. But we have the information that at time equals 1, the temperature of the object is 45. So we can plug in that information. So you get 45 degrees is equal to 30 times e to the RT, T is 1, plus 70, and then we can solve for the R because this is the equation with R that's unknown. So I'm going to quickly solve for R. So 45 minus 70 on both sides. So 45 minus 70 is 25 negative equals 30 e to the R and I'm going to divide by, oh, wait a minute. Am I running into trouble here? All right, you know what? I think I screwed up with this example, at least the way I'm trying to solve it. Because I'm encountering a problem here. Because I have a negative value, which shouldn't happen. So negative 25 over 30 equals e to the R. So that shouldn't happen. I definitely screwed up with this example. That's not good. I apologize for that. Okay. All right, you know what? I'm going to leave this example. I'm not even going to continue with this because clearly I'm running to a bad situation here. I think I'm going to come back to this example tomorrow, unless does anyone know how to help me fix this problem? If you do know, let me know. Otherwise, I'm going to leave this problem the way it is, and I'm going to come back to it tomorrow. Is that okay with everyone? Okay, sorry about that. I should have more. I've tried this earlier. Oh, you know what? That's my problem. Sorry, I just realized what the problem is. The problem is it's A here. So the difference between the object and the surrounding, that's not 70 minus 40. So the A, the difference between the object and the surrounding, I'm so stupid here. So that's going to be, the object is 40, the surrounding is 70, so that's negative 30. So that will fix the problem. So A is T object minus T surrounding. I did completely the opposite. So that's negative 30, and that should fix the issue here. Sorry about that. And now we can simplify this. So negative 25 divided by negative 30. So we get e to the R, which is positive, which we need it to be positive because exponential growth. E to the any number is always going to be positive. So that's going to be 5 over 6, which is going to add natural log on both sides here. And if we add natural log on both sides, we get R left on the left side because natural log and an E cancels. We get R equals natural log 5 over 6. So that will be the rate. As you can see earlier, if I didn't fix the issue with the negative 30, I end up with a negative number. That could not possibly be in the natural log, right? So we're going to have a problem. So here we have the R is natural log 5 over 6. And we can put back into the formula. We get T of T, the temperature of the object, is equal to negative 30, E raised to the natural log 5 over 6 times T. So that's all in the exponent plus 70. And this is going to help us answer the question. It says, how long does it take for the water to reach 60? So now if we plug in 60 for the temperature of the object, the pitcher, and then we can solve for the time. So we get 60 equals negative 30 e raised to the natural log 5/6 times t in the exponent plus 70. And then if we subtract 70, we get negative 10 equals negative 30 e raised to the natural log 5/6 t. And we can divide by negative 30 on both sides. So we get 1/3. So negative 10 over negative 30 equals this exponential part. Right? And that's 1/3 equals e raised to the natural log 5/6 t. And if we want to get the t out of there, we have to add natural log on both sides again. So we get left side, we get natural log 1/3. That's equal to, when I add a natural log to the exponential part, so natural log of e raised to the natural log 5/6 t. So the natural log and e cancels, just give me a natural log on the right side. So left side, I get natural log 1/3. That's equal to the right side, which is natural log 5/6 times t. I can solve for t by dividing by both sides by natural log of 5/6. So we get t equals natural log 1/3 divided by natural log 5/6. So that's the time. Okay. Does that make sense, the process? I know that the beginning could be really confusing to you when I made a mistake to find A. Hopefully that clarifies the issue there. So the problem with this is really just take what we know, plug in there, and to find out that, oh, we're actually missing the rate. So we need to find the rate first. After we solve for the rate, we need to put it back into the formula to get the actual formula for cooling. In this case, we're heating up the water. And then we're just going to use the final information given, the temperature equals 60, try to figure out how long does it take. So we're solving for two things really throughout the same process. One is solving for the rate in the exponent. The second part is solving for the t in the exponent. All right, any questions on this example? All right, so the next example I have is logistic growth model. So a logistic growth model has a formula of f of t equals c over 1 plus a e raised to the bt. So the c here, well, c is called the carrying capacity. And the c over 1 plus a is the sort of like the initial value, the starting value, because if we put t equals 0, e to the bt is going to be e to the 0, that's a 1. So we end up with c over 1 plus a. So this is like the initial starting value. And a typical graph of logistic growth model looks like this. So it's going to grow up, sort of like an exponential growth, but then eventually it's going to reach a plateau, like a horizontal asymptote there. And this part is reaching the carrying capacity. So this is the exponential growth in this bottom part. but it's going to reach this carrying capacity. And that's kind of like the carrying capacity in this case is kind of like the limiting factor, right? Because it can, if it continues to grow without limitation, then it's just going to exponential growth all the time. But sometimes the growth is restricted when it reaches to a certain point. For example, if we look at a population growing on an island, the population cannot possibly just grow exponentially because eventually it's going to run out of food, it's going to run out of resources, and that food and the other resources, they kind of like the limiting factor. So the population has to kind of reach a certain maximum. So that's another way to think about it. All right. So you've probably seen this before, but even if you haven't, we can look at it together. And I should point out that the B here, so B is called the logistic growth constant. All right, so that's a B. And if we know the initial value, if we know the carrying capacity, we can solve for A. All right, so here's the second example that I took from the book, well, sort of. Let's see, just gonna cut this whole thing. And let's put it here. All right, so this example says, suppose a community of 10,000 people. At t equals 0, there's one person with COVID-19. And the logistic growth constant B is equal to 0.6. It says, estimate how many people will have COVID-19 after 10 days. So let's just, so this one, we're definitely going to use this logistic growth model above. So we know the formula we're going to use is going to be f of t equals c over 1 plus a times e raised to the dt in the denominator. And we need to know the c, we need to know the a, the b, right? And we also need to know the population of people with COVID after 10 days. So let's worry about that second part later. Let's just see if we have a formula with a, b, and c. So in this example given, it says a community has 10,000 people. So we know that no matter how quickly the virus spread, and it's not going to reach more than 10,000 people, right? Because that's the maximum number of people here could be infected. So the carrying capacity, C, is equal to 10,000. So that's the max number of infected people. It cannot reach above that. So this is the carrying capacity. Okay, and also it says at t equals 0, there's one person has COVID. So f of 0 equals 1, and you know that at t equals 0, whatever we get, so that will be the initial value, right? Time equals 0, the quantity corresponding to initial value. So this is the initial value. And we know earlier, we know that c over 1 plus a is also the initial value. So in this case, c over 1 plus a must equal to 1. And we know c, which is 10,000, we can solve for a. So I'm going to plug in 10,000 there. So 10,000 divided by 1 plus a equals 1. So multiply the denominator to the right. So 10,000 equals 1 plus a. So a equals 9,999. So that's A. And then we know that B is a logistic growth constant, and in this case, it's given. So B is given to be 0.6. So now we can take those values, those constants, put into the function. So we get f of t is equal to C, 10,000, divided by 1 plus A, which is 9,999, and E raised to the B is 0.6 T. So that will be the logistic growth model for this situation. And the question says, estimate how many people will have COVID-19 after 10 days. So we know the time is going to be 10. We just need to know the population. So we're going to take 10, put in there. So we get f of 10 is equal to 10,000 divided by 1 plus 9,999, e to the 0.6 times 10. And we really need a calculator in order to get a good estimate. But suppose I don't have a calculator, I'm going to leave it as 1 plus 9,999 and e to the 6th power. And that will be the population. Any questions? All right. If you don't have questions, I think, just make sure. So that's all the exponential and the logarithmic models. So I'm going to move on to the angles. So now we're going to switch gear to talk about angles and the sine and the cosine trig functions. All right, 5.1 angles. You do have to know this sections for the exam, but I feel like for a lot of you, a good amount of this is just review because you have seen this in probably geometry, algebra 1, algebra 2, and maybe if you have taken a high school pre-calculus class, you definitely seen this before too. All right, so angles. So we know that angles could be measured in 2 different units. Just kind of like a length could be measured in feet, meters, or some other units. So angles, usually they are measured in degrees. We use this like a little circle notation, or radians. Don't get confused with radians. I know it's so difficult. Now, radians does not have to do with pi. Usually the angles we're familiar with, they come with pi in it, right? Pi over 3, pi over 4, pi over 5. But radians, the angle measurement radians does not have to do with pi. Don't get confused there. Just the unit. Radians are just units. And for a full circle, a full circle can be measured as 360 degrees. Or if we measure that circle in radians, and that's going to be 2 pi radians. Now I want you to think about the radians and the degrees are just units. 2 pi happen to be a really nice, it's just the angle was being written in terms of pi, but it's not because of pi radians, it's because of the angle itself. It's measured conveniently in terms of pi there. So a circle has 360 degrees or 2 pi radians. So we sometimes write 360 degrees is equal to 2 pi radians. So that's a conversion that you can remember. And if we divide by 2, we get 180 degrees equals pi radians. That's also another conversion to remember. All right. With that said, and then we can work on examples to convert degrees to radians, radians to degrees. But let's do that. Well, let's see. Let's do it now. So convert the following angles. So let's say convert 5 pi over 18 radians to degrees. So suppose I want to convert 5 pi over 18 radians to degrees. What I'm going to do is I'm just going to write down 5 pi over 18 radians first. And I want to convert this to degrees. The way I do the conversion is I multiply a ratio based on the conversion. So the conversion says 360 degrees equals 2 pi radians, or 180 degrees equals pi radians, right? Doesn't matter which one to use. So I'm going to take those two values, I'm going to put them in terms of a ratio. But I want to line them up correctly so that the radians will cancel, because I want to end up with degrees, right? So I'm going to put pi radians in the denominator, and I'm going to put 180 degrees in the numerator. That way, the units radians will cancel. So I end up with 5 pi times 180 degrees divided by 18 times pi. There's no more radians left. And I can try to simplify this further. Pi and the pi cancel, 18 and the 18 cancel. That gives me 10 left in 180. So I just end up with 5 times 10 degrees, that's 50 degrees. I just want to point out, this is how I usually set up the conversion, by multiply by a ratio. We just have to know where we're going to put the 180 degrees and where we're going to put the pi radians, because we're just going to line them. It's not always going to be degrees on top. It depends on what's given. So the next example I have is to convert, let's see, 130 degrees to radians. Well, let's see, negative 130 degrees. If we could have a negative angle to radians. So what I'm going to do is I'm going to begin with negative 130 degrees. Now, it's not in the denominator, right? The denominator is 1, so the degrees is in the numerator. So I'm going to multiply by this ratio from the conversion in such a way that I want the degrees to cancel. So 130 degrees is in the numerator, so I'm going to put 180 degrees in the denominator and the pi radians in the numerator. In this lineup, the degrees will cancel, and I end up with negative 130 times pi radians in the numerator. In the denominator, I only have 1 times 180. And I can try to simplify this. It looks like the zeros, the 2 zeros from numerator and denominator to cancel. So I end up with negative 13 pi over 18 radians. Any questions about converting the units? Really, like I know that a lot of us don't like radians, right? Because of pi. Now, I always think about, okay, radians is just a unit. Like if I say, okay, convert from feet to meters, you know exactly what you should be doing, right? You just find the right conversion, and then you line them up correctly, cancel the units to get the correct unit you want. Same thing here, you know, if we want to get rid of degrees, end up with radians, we're just going to line them up correctly. All right, so that's a conversion. Now, angles in standard form. Standard position are usually measured from the positive x-axis. So in the standard position, the angle will be drawn with one terminal on the positive x-axis, and it's going to go counterclockwise to a second terminal. So this will be the angle that we talk about. So that's the angle. So let me write. So start from one terminal on positive x-axis, go counterclockwise. So that's how we normally draw the angle in the standard position. That will give us a positive angle and a negative angle. So this is the, let me write, this is the positive angle. Now, what is the negative angle? How do we draw it? A negative angle, again, it's going to start from the positive x-axis. It's going to go clockwise. So this is a negative angle. It doesn't matter whether it's a positive angle or negative angle. We're always going to begin on the positive x-axis as the first terminal side of the angle. And then we're just going to go, depends on the sign, we're going to go the correct direction until we get to the right terminal side. And for example, if I were to graph the two angles above, so example graph the two angles, we have 5 pi over 18 and negative 130 degrees. If I were to plot them, let's plot 5 pi over 18 first. So the first thing I'm going to do is I'm going to begin with this positive x-axis, and I'm going to go 5 pi over 18. Right? I know that this is a 180 degrees, so that's pi. And halfway between, this is pi over 2. If we take pi, we divide it into 2, that's pi over 2, that's about 90 degrees. Pi is, we know, 180 degrees. Now, where is 5 pi over 18, right? You probably wondered. Well, pi over 2 is 9 pi over 18, but we want 5 pi over 18. So that's a little bit more than half of 9 pi over 18. So that's probably gonna, if I were to do my best, so the angle is probably right here. So this is gonna be 5 pi over 18. But as you can see, we begin with positive x-axis. We're gonna go counterclockwise until we reach to the correct place, 5 pi over 18. And if I were to plot the negative 130 degrees, so I'm going to start with the same terminal, the same positive x-axis as my initial terminal. I'm going to go clockwise, going this way. I have to stop at negative 130. So this is negative 90 if I go in the clockwise direction. 180 is negative 180 in the clockwise direction. And then if I keep going, that's going to be negative 270, and it continues. But I don't need to go that far. I only need to go all the way to negative 130. So negative 130 is 90 plus 40. So I'm going to imagine it's probably right here. So this is a negative 130 degrees. That's to graph the positive and negative angles. Any questions on this? All right, the next thing I want to talk about is called reference angles. We have to use reference angles later on when we try to find the trig function, sine and the cosine. So reference angles is the angle between all right, let me label two things. So the positive x-axis, that's the initial side, initial terminal. Well, that's not initial terminal, the initial, I shouldn't use one terminal. Starting from one side on the x positive. So that's the initial side of the angle. And then where we end up with, that's the terminal side. I should do better on this, of the angle. So the angle, so the reference angle is the angle between the terminal side and the x-axis. So we take the terminal side of the angle in standard position, and we're going to just create an angle using that terminal side and the x-axis. Doesn't matter. It's just the closest side of the x-axis. For example, when we had a angle earlier, that's 5 pi over 18. This is the terminal side. This is the initial side. And if I use the terminal side and under the x-axis, I'm going to create an angle. So this will be the angle I'm going to create because I'm using the closest side of the x-axis under the terminal side. So this is called the reference angle. And in this case, the reference angle happened to be the same, happen to have the same measurement as the given angle 5 pi over 18. That's not always the case. For example, the second example I had, negative 130 degrees. So that's the terminal side. This is the starting side, the initial side. And if I were to use the terminal side and then the x-axis, I'm going to use the negative x-axis because that's the closest to the terminal side. And this angle created between those two sides. So that's going to be the reference angle. And this reference angle is not going to be 130 degrees. It's going to be the difference between 180 degrees and the 130. So that's equal to 180 degrees minus 130 degrees equals 50 degrees. As a general rule, the reference angle is always going to be from 0 to 90 degrees or 0 to pi over 2. So always between 0 and 90 degrees, pi over 2 radians. The reference angle is not going to be more than 90 degrees. So that's a reference angle. Okay. So the next thing to go over is coterminal angles. So that just means that two angles end up with the same terminal side. So that means angles share the same terminal side. So you probably wonder, okay, if we draw an angle, for example, this one, 5 pi over 18. So that's the terminal side. You probably wonder, okay, how can we draw another angle with the same terminal side? Wouldn't that be the same angle if I draw it this way? That is correct if we draw it that way we just end up with the same angle, right? But we don't have to stop there. For example, if I draw a angle, let's see, starting with positive x-axis, I'm going to go past that and then come back to it. So the second angle I draw using the yellow arrow there. So that angle and the initial angle 5 pi over 18, they end up with the same terminal, but they're different measurements. How big is this second angle I draw here? Well, that's going to be a full circle plus 5 pi over 18. So that's a 2 pi plus. So this is 2 pi plus 5 pi over 18. So that's how big it is, because it's a full circle and then 5 pi over 18, more than that. We could also take another angle and just keep going in circles, and then eventually, after many circles, we end up with the same terminal side. That's fine too. But if we added one more circle, we just end up with adding 2 pi to the angle. So generally speaking, coterminal angles. So let's see. So suppose this angle is theta. So coterminal angles of theta has measurements of theta plus 2 pi times k, where k is an integer. So it could be 2 pi if k is 1, 4 pi if k equals 2, 6 pi if k equals 3, right? So this depends on how many circles we're going to add to it. But in this case, k could also be negative. K doesn't have to be positive. If k is negative, we just have 2 pi, the angle minus 2 pi. So that will be the case when we have a negative angle. For example, if I draw this angle starting positive x-axis and then go clockwise to that terminal. So how big is this angle? Well, that angle is going to be the difference between 2 pi and 5 pi over 18, but it's a negative. So it's going to be negative. So let me write down. So that's going to be negative 2 pi minus 5 pi over 18. So that's the same thing as 5 pi over 18 minus 2 pi. It's a negative angle because it's going clockwise, but the difference between the value, the amount, the magnitude for the angle is the difference between 2 pi and 5 pi over 18. So we can think about is the difference between 5 pi over 18 and the 2 pi. Now, if we have that negative angle, but instead of stopping that, it just continues after it passes a full circle, and then it comes back to that, right? So again, it's just like a negative, more negative. How much more is like an extra negative 2 pi. So that's going to have a value of 5 pi over 18 minus 4 pi. As you can see, it's always going to increase or decrease by multiples of 2 pi, whether it's in the positive direction or the negative direction. So you can think about it as theta plus 2 pi times k, where k could be positive or negative, or you can think about it as theta plus or minus 2 pi times k, but k only being positive in that case. So let's see. Or you can think about it as theta plus or minus 2 pi times, I'm going to use n, where n equals 0, 1, 2, 3, if you want to restrict n to be whole numbers. But either way, it's good to think about this. All right, here's a couple examples we can look at. So, example, find a positive coterminal angle of negative 130 degrees in radians. So we're going to look at this negative 130 degrees, and we want to find a positive angle that shares the same terminal as negative 130 degrees, but we want the angle to be in radians. Well, in this case, it's probably better to begin with radians. So note, we had negative 130 degrees is equal to 13 pi over 18 radians. We found this earlier, right? So we're just going to, instead of using negative 130 degrees, I'm going to use 13 pi over 18 radians. Sorry, negative. And then we want to find a positive. So this is a negative angle, but I want to find a positive coterminal angle. So I'm going to keep adding 2 pi until I reach positive. So the coterminal angle is going to be negative 13 pi over 18 plus 2 pi. Is that going to give me positive? If it is, I don't have to add another 2 pi. So let's see, that's a negative 13 pi over 18 plus 36 pi over 18. Looks like that's going to be 23 pi over 18. That is positive, so we're good. If we add 2 pi, we end up with negative again, then we just keep adding multiples of 2 pi until we reach a positive angle. All right, the second example I have is find a coterminal angle of, let's see, the angle I have is um, 29 pi over 3. So we're going to find the coterminal angle of this, but we want this coterminal angle is between 0 and 2 pi. So if we just want a coterminal angle, we can add 2 pi, we can subtract 2 pi, it doesn't matter, right? We're going to end up with a coterminal angle. But in this case, we want to find the coterminal angle so that it's between 0 and 2 pi. Well, by just first looking at it, we know that 29 pi over 3 is a pretty big number because it's 29 in the numerator. So I'm going to subtract 2 pi to begin with. So 29 pi over 3 minus 2 pi. Let's solve for this angle, say if it's between 0 and 2 pi. So that's going to be 29 pi over 3 minus 6 pi over 3. So that's going to be 23 pi over 3. It's still pretty big. And then I'm going to keep subtracting 2 pi. So 23 pi over 3, so minus 2 pi again, so minus 6 pi over 3. So 23 minus 6 pi. So 23 minus 6, that's a 17 pi over 3. Again, that's still going to be more than 2 pi. So this is more than 2 pi, 6 pi over 3, or 2 pi. Again, this is going to be more than 2 pi, or 6 pi over 3. We'll just keep going. So 17 pi over 3 minus 2 pi, or minus 6 pi over 3. So that's going to be 11 pi over 3. Again, that's still going to be more than 2 pi. And then we keep going. 11 pi over 3 minus 6 pi over 3, 2 pi. So that's going to be 5 pi over 3. And it looks like 5 pi over 3 is actually less than 2 pi. And it's definitely more than 0 because it's positive. So if we found it. So we get 5 pi over 3 is the correct answer. I just want to use this example to show you that a problem like this, sometimes you're not going to end up with a lot of problems like this, but you might. That we just have to keep subtracting 2 pi multiple times until we get the right coterminal angle we desire. Okay. Any questions on this? All right. Let's see. Let me go through two small concepts, and I think we can take a break after that. So the next thing, since we talk about gradients, it's sometimes going to help us. Let's see. Oh, wait a minute. Maybe we should change this a little bit. No, that's okay. All right. So the next thing I want to talk about is arc length and area of sector. So suppose theta is a central angle in radians. So here I have an angle as a central angle because the vertex of the angle is at the center of the circle at the origin. So this is theta. And suppose the angle is measured in radians, then the arc length corresponding to this central angle, which is this part, I'm going to call it S. So the arc length S is equal to R times theta. But theta must be in radians. If theta is not, radians. If theta is not in radians, then we cannot use this equation. And the area, this sector has the area. So this is the sector with the area. I'm going to call it A. So area of the sector is equal to 1/2 R squared theta. Again, theta is in radians. With theta in radians, it's a lot easier to calculate the arc length or area of sector. Now, if you are given the theta is in degrees, all we have to do is convert the degrees to radians first and then use it in those formulas. So for example, so suppose we have a central angle of, let's see, 25 degrees. I don't even need this grid. I just say this is a circle and this is 25 degrees central angle. So the question is, what is the arc length? And what is the area of sector? For this sector right there. So in this example, the theta is 25 degrees and it's not in radians, and I cannot take 25 put into the formula directly, right? Oh, I forgot to tell you that the radius is, let's see, the radius is 2. Right, I cannot just take 2 times 25. That's not correct because the units are not correct. So what we have to do is we have to convert theta to radians first. So convert theta to radians. So that's going to be 25 degrees times a conversion. I want the degrees to go away, so I'm going to put 180 degrees in the denominator, pi radians in the numerator. So that give me cancellation of the unit degrees. And now I can simplify 25 over 180. So So 25 pi radians over 180. If I simplify that, divide by 5, so that's a 5, 3, 6. So I get 5 pi over 36 radians. Since I already know the radius is 2, I can find the arc length. So S equals R theta. So that's going to be 2 times 5 pi over 36. Cancel the 2 into the denominator, so we get 18. So we got 5 pi over 18. So that's the arc length. And if I want to know the area of sector, so that's going to be 1/2 R squared theta. Again, we're just going to use the theta in radians directly. So that's a 1/2 times 2 squared times theta, 5 pi over 36 radians. So that's going to be 1/2 times 4 times 5 pi over 36. Now, with the example I took, it happened to be 5 pi over 18 again. I hope that doesn't cause any confusion. It just somehow, with the example I have, radius equals 2, and then we end up with this number. They don't show up for any other particular reasons. Okay. Does that make sense? Any questions on this? So I suppose that you have seen most of it already. Again, just probably review. But let's see. Any questions before we take a break? Okay. All right. Let's take a quick break. By 7:12. Let's see. Be back here by 7:20. All right. So let's take a break until 7:20. All right, welcome back. I have to fix another error in my note. I'm so sorry to say. So earlier when we were talking about the logistics growth model, I had a mistake in my formula. So I wrote f of t equals c over 1 plus a e to the bt, and that really should be e to the negative. I'm so sorry for that. But anyway, you're not going to ask to memorize this formula. You will be given, if I give you a problem on logistics growth, you're going to be given the formula, and then you can just try to figure out the correct constants and put in there. Yeah, it shouldn't affect the process much except for the answer at the end. So it's e to the negative dt, e to the negative 0.6 t, and the negative e to the negative 6. Otherwise, we're going to have a problem there. So that was my issue with this formula. All right, so if you took notes, please correct them accordingly. All right, on that note, any questions? Okay. I think in the homework, you're going to have one logistic growth question. I believe the formula is already given. You just plug in the right quantity t, or maybe solve for t, one of the. All right, so let's continue with our lesson today. So the next thing we're going to talk about is unit circles. So a unit circle is just a unit circle. It's a circle with radius equals 1. And we like to use unit circles because it makes the process of finding sine and cosine a lot easier for a lot of angles. You probably know how to find sine and cosine for 30, 45, 60 degrees using the special right triangle. But with unit circles, it's make it easier to find angles that's more than 90 degrees, or any angle basically that we can. That's a multiple of 30, 45, or 60. All right. So first, let's plot some angles. So note. So pi over 6 radians is equal to 30 degrees. Pi over 4 radians is equal to 45 degrees. And pi over 3 radians is equal to 60 degrees. And pi over 2 radians is equal to 90 degrees. And pi is 180. So those are considered as the convenient angles, the nice angles. So we can use them to plot a lot of angles on the circle. So let's see, this is my unit circle with radius 1. So this is a 1, this is a 1, negative 1, negative 1. And I'm just going to plot those angles. So pi over 6. So the way I do it is I know that this is a 0 if I'm starting on the positive axis and ends there. Doesn't go anywhere. So that's a 0 radians. And if I cross to the other side, so I end up with pi radians. And if I pass pi and come back to 0, so I get 2 pi. So either 0, 2 pi, 4 pi, multiples of 2 pi are always going to end up with the same place. All right. So the way I think about it is, okay, from 0 to pi, halfway between, I should get half of that, right? So that's a 0 to pi, that's pi over 2 radians. And then I'm thinking, okay, from pi over 2 to pi, that's another pi over 2. So if I want to count in terms of pi over 2, so I get pi over 2, 2 pi over 2, so that's pi, and then 3 pi over 2. So I get to this point, 3 pi over 2, and then 4 pi over 2, which end up with 2 pi. So that's how I count in terms of pi over 2. And then I can think, I'm going to do is I'm going to find the halfway between pi over 2 and the 0. So if I count between pi over 2 and 0 and a pi over 2, halfway between, I get this one. So that's like a half of pi over 2. So that's pi over 4. So I can think about, okay, I'm going to count in terms of pi over 4 now. So I get 0, that's pi over 4, 2 pi over 4, that's pi over 2, 3 pi over 4, that's here. And if I keep counting, that's a 4 pi over 4, 5 pi over 4. So this point is 5 pi over 4. And then 6 pi over 4, which is the same thing as 3 pi over 2. 7 pi over 4 is here. And then 8 pi over 4 end up with 2 pi. So that's how I end up with angles 7 pi over 4, 5 pi over 4, 3 pi over 4, and pi over 4. Just count in terms of those units. And then I can count, okay, I know that pi over 4 is 45 degrees. Pi over 4 radians is about 45 degrees. Now, pi over 6, which is 30 degrees, so that should be a little bit less than pi over 4. So I'm going to plot that. So less than pi over 4, maybe somewhere here. So that's going to be pi over 6 radians, or 30 degrees. And I can try to count in terms of pi over 4. So I get from here, pi over 4, 2 pi over 4. Sorry, my fault. So pi over 6, if we can count in terms of pi over 6, so we get pi over 6, 2 pi over 6. Now 2 pi over 6 is the same thing as pi over 3, so that should be pi over 3. And if I keep counting, though, that's 2 pi over 6, and then 3 pi over 6 take me to pi over 2. So let me put it here. So pi over 6, 2 pi over 6, 3 pi over 6, that's pi over 2. And then 4 pi over 6 leads me to here, which is, so if you write 4 pi over 6, that's the same thing as 2 pi over 3. So this is 2 pi over 3. And then keep going. So that's 4 pi over 6, and 5 pi over 6 should be here. So this is a 5 pi over 6. And keep going. 6 pi over 6, that take me to pi. And then past that, so that's a 7 pi over 6. 7 pi over 6. And then 8 pi over 6, that's going to pass 5 pi over 4. So this is the 8 pi over 6, which is the same thing as 4 pi over 3. And then I keep going, 9 pi over 6 take me to 3 pi over 2. And then passing that, I get another pi over 6. So that's going to be 10 pi over 6, which is 5 pi over 3. And if I keep going, the next angle I'm going to have is 11 pi over 6. Then I keep going, I get 12 pi over 6, which is the same thing as 2 pi. So that's how I usually look for those angles. I try to count them in terms of multiples of pi over 4, pi over 6, sometimes pi over 2, sometimes pi over 3. So as you can see, you don't really need to memorize all the angles on the circle. You just have to know, okay, if it's a multiples of pi over 6, I'm going to count in terms of multiples of pi over 6. If it's multiples of pi over 4, so I'm going to count in terms of multiples of pi over 4. All right, are there any questions about how I end up with those angles? I guess another note about pi over 3, you can think about that. So pi is 180, right? So this is a pi. If we divide it into 3 parts, so we get this. Each of them is pi over 3, 2 pi over 3, 3 pi over 3, take us to pi. So that's a quick way to think about multiples of pi over 3. You look at the the straight angle 180 degrees or pi radians, and divide it into 3. Oh, maybe I have to leave it there. So you can think about, okay, that's pi over 3, that's 2 pi over 3, this is 3 pi over 3, 4 pi over 3, 5 pi over 3, and then I go back to 6 pi over 3, just to reiterate. All right, so that's angles on the unit circle, and we're going to use this in a couple of minutes to find sine and cosine. And there's a very important thing to note about points on the unit circle, just like the one we draw earlier with this angle. So suppose we just have a random point. So for a point on the unit circle, so it's still a unit circle, 1, 1, -1, -1. Let's just see, I don't have to land on the the convenient angles we had. Just say we pick a point, let's say it's right here. So this point has a coordinate x, y. And if I draw the radius is 1 here, right? And if I create a right triangle by using that point and the x-axis, so I get this small right triangle, looks like this. I'm going to recreate it on the side. So that's a radius of 1. This is the origin. So I get this right triangle. And let's see this angle here is theta. So I'm trying to draw the theta is where the angle. So this is theta. And okay, so you probably wonder, if I want to know how long is this side or the vertical side, can I find it? Yes, we can find it. So let's call this x because it's in the x direction. Let's call this y, it's in the y direction. So using SOHCAHTOA, we can find x because we know that x over 1, the adjacent to this angle divided by hypotenuse, that's equal to cosine theta multiplied by 1. So we get x equals cosine of the angle theta. And similarly, we can find the y by using sine theta equals y, the opposite, divided by hypotenuse 1. So we get y equals sine theta. And it turns out that that's always true for unit circles. So if you have a unit circle and you have a point on the circle, the x coordinate is always going to be the cosine of the central angle. The y coordinate is always going to be the sine of the central angle. So this x here is always going to equal to cosine of the angle, the central angle. The y is always going to be sine of the central angle. That's how convenient it is. If we just want to see, let's see, we have angle theta, we want to know what the cosine of the angle is, and we happen to know the x coordinate of the on the circle, on the unit circle corresponding to this angle, we can just say, okay, the cosine theta is equal to this x value. So you have to, at this point, you have to think about sine and cosine in terms of x and y. Well, y is a sine, x is a cosine. Obviously, if you try to think about in terms of SOHCAHTOA, that's still useful. But that's like a limited to right triangles. But you have to think about sine and cosine in terms of y coordinate, x coordinate on the for points on the unit circle. Right. So here comes a very well, one more thing before I move on. So you probably think, okay, what about tangent theta? Well, tangent is the opposite of adjacent if we have a right triangle. Suppose we don't have it. That's just going to be y over x if we look at this triangle. That's the same thing as sine theta over cosine theta. So this is more useful than opposite of adjacent. When you think about tangent theta, try to think about sine over cosine. And then here's the important trigger identity that you're probably seeing it so many times. If we look at, let's see, suppose we take this triangle, we just look at the triangle. If we look at the right triangle here, we have Pythagorean identity, which is x squared plus y squared equals 1. But remember that x is just a cosine theta, so we got cosine theta squared plus sine theta, which is y squared, must equal to 1 if we substitute for x and y. Another way to write it is cosine squared theta plus sine squared theta is equal to 1 for all theta. So for all theta, it could be 5, it could be 100 radians or 100 degrees, doesn't matter. As long as the angle is the same in the sine and the cosine, it's always going to satisfy this equation. And this identity could be useful sometimes to help us find some of the trig ratios, for example. So suppose we know that sine, we don't know what angle is, but we know that sine theta equals 2/3, and the angle is in the angle is between pi/2 and pi radians. Find cosine theta. Of course, you say, okay, I have a calculator, I can just put this into the calculator. Absolutely, that's the right way to do, right? To find theta, if you know how to find theta using inverse sine function, and then after you get the theta, you find cosine theta. That's one way. Suppose we don't have a calculator, and it's not a nice value, right? Sine of what angle give me 2/3 is none of the 30, 45, 60 degrees. How do we find it? Well, we can use this Pythagorean identity, the trig identity above. So we know that cosine squared plus sine squared equals 1. So we can plug them in. So we get cosine squared theta. I don't know what cosine theta is, but I know that square is going to, when we add sine squared, so that's a 2/3 squared, that's going to give me 1. That's what I know. So if I solve for cosine theta by subtracting 2/3 squared, I should be able to find it. So cosine squared theta equals, plus 4/9 equals 1 minus 4/9. So we get cosine squared theta equals 1 minus 4/9, which is going to be 5/9. And then take square root on both sides, get cosine theta equals plus minus square root of 5/9. That's going to be plus minus square root of 5/3. So now we have two values for cosine theta. You probably think, okay, which one is correct? Are both correct? So this is where we have to go back to the given. We have to consider the angle is between 2 pi and the pi radians. So if I quickly draw the unit circle, this is pi/2, this is pi. I know the angle is somewhere in the second quadrant here. Okay, is a cosine going to be positive or negative? But remember, cosine is x. So recall x equals cosine theta. And if the angle is in the second quadrant, so if I just say, let's say I pick this point, doesn't matter, right? Somewhere a point on the circle in that quadrant. Is the x going to be positive or negative? And we know in the second quadrant, the x value, the x coordinate for any point is always going to be negative. It's not going to be positive. So therefore, we have two cosine values. When we pick, we're going to pick the negative one, the negative value. Therefore, the correct cosine theta is going to be negative √3/3 because the angle is going to be from pi/2 and a pi. So we have, so that's the way to solve it. We have to be very careful with the sign as IGN. So we have to be careful with sine. Let me just write down. Be careful with sine, whether it's positive or negative at the end. Even though we can follow the same equation, the same formula, and then carry out the every step correctly, we have to be careful whether we're going to choose a positive value or negative value at the end. All right, any questions on this?
Is it negative root 3 over 3 or negative root 5 over 3?
I'm so sorry, negative root 5 over 3. Thank you, good catch. All right, so that's using the trig identity, the Pythagorean identity, to find the Pythagorean theorem to find the cosine. And if we know the cosine, we can find tangent. So suppose the question says find tangent theta. We can do it because now we know sine, we know cosine, right? So tangent theta using the, instead of opposite over adjacent, we can use sine over cosine. And to plug in the sine value, which is 2 over 3, plug in the cosine value, which is negative root 5 over 3. And we just, all we have to do is multiply by the reciprocal of the denominator. So that's a 2 over 3 times negative 3 over root 5. So the 3 cancels, give us negative 2 over root 5. We have to be careful. We don't like square roots in the denominator. So to simplify further, we multiply by square root of 5 to both numerator and denominator. We end up with negative 2 root 5 over 5. So that's the tangent. All right, any questions on this? So the next thing we're going to do is we're going to use unit circle to figure out some sine and cosine values of nice angles. So use unit circle to find trig functions, sine and cosine of some nice angles. But before we do that, I'm going to just, you probably all remember this in the past, some special right triangles. So recall special right triangles. I don't know which version you memorized, but you definitely memorized that. So let's see, this is 30 degrees, 60 degrees, 90 degrees, and 45, 45, 90. Now you probably remember for the 30, 60, you get x, 2x, root 3 over x, right? There's no point to keep all the x in this. So you can just remember 1, 2, root 3. But that's not going to help us much because we're working with the unit circles. A lot of times, if we draw a right triangle, the hypotenuse is going to be 1. So I'm going to divide every side by 1, but sorry, by 2. So I get 2 divided by 2 is 1. 1 divided by 2 is half. Root 3 divided by 2 is root 3 over 2. So this is very important to remember as a special right triangle. So if you don't have it memorized in the past, you definitely need to do it now. Hypotenuse must be 1. And the side opposite from 30 is going to be half. The side opposite from 60 is going to be root 3 over 2. Have it memorized. It's going to be very useful. And for the 45, 45, 90 degree right triangle, so you probably remember 1, 1, root 2, or something like that. But I don't want the hypotenuse to be root 2. I need it to be 1. So I'm going to divide by root 2 on all sides. So I end up with hypotenuse is just 1. Well, what about the 2 legs? It's 1 over root 2, but we don't like to write this. We're going to write root 2 over 2. That's the same thing as 1 over root 2. So again, memorize this special right triangle. So for the 45, 45, 90, it's going to be root 2 over 2, root 2 over 2, and 1 on the hypotenuse. 30, 60, 90, we get 1/2 root 3 over 2 and a 1 on the hypotenuse. Those numbers are very, very convenient for the rest of what we're going to go over today and also next week. So let's see. Memorize if you haven't. All right. So we're going to use those special right triangles, and let's begin with the first example. So example 1. So we're going to find cosine of 315 degrees using the unit circle. So a problem like this, you're not allowed to use the calculator, so just be comfortable with the process. So the way I do it, so step 1. So we're going to graph the angle on the unit circle. So we need to know where the angle is on the unit circle. So this is my unit circle. This is a 1, that's a 1, -1, -1. All right, so 315 degrees. Do your best, right? It's pretty close to 360 degrees. So if we begin, it's a positive angle. So I'm going to begin with the positive x-axis. So I'm going to go around almost 360, definitely more than 270. So 315 is going to be 45 degrees more than 270. So that's probably going to be here. So this point on the unit circle corresponding to this angle, that's 315 degrees. Right? So that's the first step. The second step, we're going to use that point on the circle. We're going to create a right triangle using x-axis. So what we do by creating the right triangle, so we're always going to use the x-axis. So what we do is we're going to start with a point. We're just going to draw a dotted line directly to the x-axis. So that's how it's going to give us a right triangle using the x-axis. So always using the x-axis, never use the y-axis. So when I do that, so that's a right triangle. Step 3, find the reference angle. And if you recall that the reference angle is the angle between the terminal side and the x-axis. Again, we always use the x-axis here. So that's going to be between, this is 315, that's 330. So that's going to be 330 minus 315. So that's going to be 45 degrees. As you can see, this special right triangle is going to be 45, 45, 90. There's no other way, right? So step 4. So we're just going to label all sides of the special right triangle. Using the measurements, I put them above. So the special right triangle for 45, 45, 90 I memorized is 1 root 2 over 2, root 2 over 2. So the hypotenuse is always 1 because that's a radius. And as the 2 legs, it's going to be root 2 over 2, root 2 over 2. And we're almost done here. So if we know the legs of the right triangle is root 2 over 2, and the hypotenuse is 1, and now we can actually find cosine. So step 5 is optional. Not necessary in this case, but sometimes it's very useful. Well, actually, I'm not going to say it's optional. So find, after you practice a lot, you can skip, step 5. So find the x, y coordinate of the point on the circle. We actually have all the values we need. So for this point on the circle, we're going to find the x and the y. Well, we know that if we start from the origin, we're going to go √2/2 units to the right. So that's going to be √2/2, and it's positive x-axis direction, so there's no need to worry about negative. And then after that, we're going to go down √2/2 into the negative y-axis direction. So that's the √2/2 units, this number. But it's negative because we are in the negative y-axis direction. So that's the xy coordinate for that point on the circle. And then now we can just figure out what the value we're looking for. So step 6, find the trig function. So here we're looking for cosine, but remember cosine is x, right? So the x coordinate is equal to cosine, the y coordinate is equal to sine. And then we're looking for cosine 315, we already have the value, √2/2. So cosine 315 degrees is equal to √2/2. I don't know how you feel. I really like this approach because I know it takes a little bit longer, but once you get comfortable with the process, it's actually pretty quick and easy to do. And there's no calculation because you memorize the 3 sides of the special right triangle. And I guess the only calculation you have to do is find the reference angle. Shouldn't be that bad. And all we do is we graph the angle, draw the right triangle, find the reference angle, decide which special right triangle we use, label the sides, and that will give us the xy coordinates, which we can use to find sine and cosine. So that's how I do it. I hope you find it easy over time. I'm not saying now, but I want to point out one important thing. When we write down the xy coordinates for the point on the circle, or even later when we find sine and cosine, but if you have step 5, it's very important. You need to make sure the sign is correct. So make sure the sign is correct, the signs are correct. If you get confused with that, just think about, okay, to make sure the signs are correct, all you have to do is make sure that, you just look at, are we in the positive x-axis direction or are we in the negative axis direction? Are we in the positive y-axis direction or the negative y-axis direction? I know in the past, your teacher probably says like all students take chemistry or something like that. I just never find it helpful. If you find it helpful, use it. That's tell you what signs are. But for me, I just look at which part of the x and the y axis I'm looking at. Is it to the left side of the origin, to the right side of the origin, below or above? So that tell me whether it's positive or negative. All right, any questions on that? Okay, we're going to go through several examples like this just to practice. So the next example I have is we're going to find sine of -pi/6. So again, the first step, I'm going to just draw a circle, a unit circle. That's a 1, this is the 1. You don't have to label the ones and negative ones if you're comfortable with it. And I'm going to plot the angle -pi/6. So I'm going to begin with positive x-axis. I'm going to draw a negative angle. So going clockwise, pi/6. So I know that this is a pi if I divide it into 6 parts. So this is a pi/2 and divide it into 3 parts, 1, 2, 3. So I get pi/6 negative. I'm not going to label it there, that point corresponding to -pi/6 angle. So I found the point after plotting the angle, and I'm going to use this point. I'm going to create a right triangle using the x-axis. Again, I'm going to go up. Always go up to the x-axis and create the right triangle there. And after I've done that, I'm going to find the reference angle. Well, it looks like the reference angle is the same angle. Doesn't have to do any subtraction. And how big is this angle? So now we're looking at not negative angle, we're just looking at how big the angle is. That's going to be 30 degrees. Because the actual angle is negative pi over 6. So the reference angle is going to be 30 degrees there. So now we have 30, 60, 90. Special right triangle. And this is 30. Hypotenuse is 1. The side opposite from 30 is going to be half. The side next to 30 is going to be root 3 over 2. So I have those three sides. If you remember that, the three sides of the special right triangle. Hypotenuse is 1. The side opposite from it, from 30 degrees, is going to be 1/2. The side next to 30 degrees is going to be root 3 over 2. So with those values, I can immediately write down what the XY coordinates are for this angle. So the X coordinate is in the X direction. If I start from the origin, I move root 3 over 2 in the positive X-axis direction. So that's a positive. And then I'm going to move down 1/2. So, but it's a 1/2 in the negative Y-axis direction. So that's a negative. And if I want to know sine of the negative pi over 6, and immediately I have, that's going to be the Y coordinate. So this is going to be my sine. So we get sine negative pi over 6 equals negative 1/2. You're probably thinking, oh, that took a while. It is true in some sense, but there's really no calculation just based on memorization. All right, let me give you another example. So we're going to find, let's see, we're going to find the cosine of 90 degrees. Suppose you don't have it memorized in the past. Let's just see, we're going to use the same unit circle to find it. So we're going to create a unit circle. And I'm just going to draw the angle 90 degrees. So I know starting here, 90 degrees is right here. There's no fancy thing going on. So that point on the unit circle corresponding to this 90 degrees. You probably wonder, okay, so from that point, I'm going to create a right triangle using x-axis. It looks like I cannot, because if I go to the x-axis, I only get a line. I don't see a right triangle. No problem. In this case, we just don't use right triangles. We don't even use reference angles, because if we have a point like 90, if we have a point corresponding to 90 degrees, it's actually really good, because we immediately know what this point, the coordinates for this point is, because that point is on the y-axis. If a point is on the y-axis, then we know the coordinates going to be, that's just going to be 0, 1. There's no other way to write down the XY coordinates other than just quickly looking at the y-axis to figure out where the point is 0, 1. And there's no right triangle, no reference angle. It actually saves a lot of work. So from here, what we can do is we can find cosine 90, because cosine, remember, it's the x. So the x value, x coordinate is going to be cosine. The y coordinate is going to be sine. So cosine 90 equals 0. It's actually a lot faster because you don't have to worry about the special right triangles. Any questions? All right, let me do, it's 8 o'clock. We're definitely going to finish early. Don't worry if you are just wondering when we're going to finish early, whether we're going to finish early and when we're going to finish it. We'll be done soon. So let's look at another example. We're going to find tangent of negative pi let's say negative 5 pi. Right, that's the angle. And we're going to find tangent of that. We have been practicing sine and cosine, but now we want to find tangent. Again, we're going to use a unit circle. First of all, I'm going to plot the angle negative 5 pi. And I know this is going to be 0. If I'm starting here, this is negative pi, and negative 2 pi, negative 3 pi, negative 4 pi, negative 5 pi. Looks like it landed right here. So this is the negative 5 pi angle. Okay, and it looks like it's already on the x-axis. There's no way to create a right triangle there. If I draw a vertical line to the x-axis, that's fine. Don't panic. So in that case, you should be like, oh, that's great, because I immediately know the xy coordinates for that point, which is going to be x is negative 1, y equals 0 for that point. This is a lot simpler, I think. Okay, so that means, remember, x coordinate corresponding to cosine and y coordinate corresponding to sine. And I need to find tangent. I know sine, I know cosine. Can I find tangent? Yes. So tangent negative 5 pi is equal to sine negative 5 pi over cosine negative 5 pi. The sine over cosine give us tangent. And I know that sine value is going to be 0 because that's what the y coordinate is for that point corresponding to the angle. And x coordinate is going to be negative 1. That's the cosine. So 0 over negative 1 equals 0. So tangent of negative 5 pi equals 0. Problem solved. All right, any questions on those examples? It works really well. It's I personally think this is a lot more fun than using the calculator. You know, you just put in the calculator, you don't really know like how to relate the final answer with the angle given. But here at least you can kind of get like some kind of picture relating them. It's like, oh, okay, just a point on the unit circle and perhaps the special right triangle. Okay, let's see. So that's sine, cosine, and a tangent. I suppose, let's see, I have one more thing that I have to talk about. Let me ask you this. Do you want another example on this, like related to find sine, cosine, or tangent using the unit circle? Let me know if you want another example on this part. All right, let's see, someone put in the chat. All right, so let's look at another example. I'm just going to pull something off my head quickly. It doesn't matter. As long as the angle is as a multiple of 30, 60, or 45. Let's see. So we're going to find tangent of how about this? Negative 5 pi over, nope, negative -8 pi over 3. So that's the angle. So the first thing I'm going to do is I'm going to draw the unit circle. That's a 1. This is a 1. -1. This is a 1. This is a -1. And I'm going to plot the angle. So the angle is -8 pi over 3 radians. So we're going to starting here, and we're going to go, okay, the multiples of pi over 3. So remember that if we have pi, so that's a 0, this is a pi over 3, 2 pi over 3, and so on, right? So pi over 3, 2 pi over 3, or if we clockwise, this is negative pi over 3, negative 2 pi over 3, negative pi. Okay, so I got negative 8 pi over 3. So I'm going to go, okay, that's a negative pi over 3, negative 2 pi over 3, negative 3 pi over 3, negative 4 pi over 3, negative 5 pi over 3, negative 6 pi over 3. Go back to the same positive axis. So negative 6 pi over 3, negative 7 pi over 3, negative 8 pi over 3 took me there. So this is the negative, so the angle is negative 8 pi over 3. And this point on the unit circle corresponding to the angle, the terminal side of the angle. Okay, good. And then what we do is we need to use the x-axis to create a right triangle. So I'm going to, starting at this point, I'm going to go directly up to the x-axis and create a right triangle there. So now we have this right triangle, and the hypotenuse is 1. I need to know the reference angle. So how big is this reference angle? That's what I'm curious, right? Well, the way to find, there's a couple of ways. One is think about, this is a negative 8 pi over 3. If I go 1 more pi over 3, I'm going to end up, so from this point, if I go 1 more pi over 3, I'm going to end up with this negative 9 pi over 3, which is multiples of pi, negative 3 pi. So the difference between the terminal side of the angle and the negative x-axis is really just negative pi over 3, or pi over 3 if we only look at reference angle. So that's going to be 60 degrees here. If that's 60 degrees, that means this angle near the point, that's going to be 30 degrees. I know it's difficult to read. So this angle right here is going to be 30 degrees. And I already know that hypotenuse is going to be 1. Because that's the radius, right? From the origin to the point, that's the radius. Okay, so now we can label the sides. So the hypotenuse is 1. The side opposite from 30, that's this side. So that's going to be 1/2. The side adjacent to 30 degrees, that's going to be root 3 over 2. With those numbers, I can write down the xy coordinate for this point. And the point, the x coordinate is going to be from the origin going half units to the left, following the negative x-axis direction. So that's going to be half unit in the negative x direction. So that's a negative 1/2. And then the y coordinate is going to be going down root 3 over 2 units. So that's going to be root 3 over 2. But it's going to be in the negative y direction. So that's a negative. So those are the xy coordinates. And they are also the cosine value and the sine value. And obviously, I'm not interested in sine and cosine, right? I want to find tangent. So tangent of negative 8 pi over 3 is going to be sine negative 8 pi over 3 divided by cosine negative 8 pi over 3. Oops. And that's going to be sine, which is the y coordinate, negative root 3 over 2, divided by the x coordinate, which is negative 1/2. So negative divided by negative is positive. You already know that. And you probably think, okay, can I just multiply by the reciprocal of the denominator? We could. But another way, that's what I did earlier, right? To find the tangent with the previous example. So I could multiply by the reciprocal of the denominator. But I want to show you another way to find this quotient. I'm going to just, looks like I have 2 in the denominator for both the numerator and denominator. So I'm just going to take the numerator, the fraction, multiply by 2. I'm going to take the denominator, the fraction 1/2, I'm going to multiply by 2. So if I multiply by 2 in the numerator and denominator, so now I can cancel the 2 I multiplied to numerator and denominator with the existing denominator of both parts. So I just end up with root 3 over 1, which is root 3. We can, like I said, we can just multiply by the reciprocal. So we could take root 3 over 2 times the reciprocal, which is 2 over 1. That's still going to give us root 3. Two ways to think about it, whichever you feel comfortable with. All right, any questions on this? Again, like I said, you've probably seen it before, but your teacher probably try to explain it the same way I did, or maybe they have a different approach to use a unit circle. Trust me, do not. So I want to show you one thing that you probably, I probably zoom it down soon here. So let's see. I want to show you something quickly. It's a unit circle. So you probably had teachers in your past like ask you perhaps, well, I'm not saying you definitely had it, but let's see. They might ask you to memorize it. So you probably had a teacher in the past ask you to like say, oops, why did I paste it? Oh, well. Hold on, just a second. Okay, you probably had a teacher say, okay, here's a unit circle, memorize the angles in degrees, in radians, memorize, those X, Y coordinates of those points, and then you probably had a quiz on them in the past too. All right, trust me, don't even bother memorizing those. Well, if you choose to, perfectly fine, you know what, go for it. I'm just saying like that you don't need to memorize, those values, because the way, at least the way I learned this is not by memorizing all those numbers and the values. For example, if I want to plot, let's see, 7 pi over 6, I just count, okay, pi over 6, 2 pi over 6, 3 pi over 6, 6, 7, 8, I lose count. Anyway, pi over 6, 2, 3, 4, 5, 6 pi, 7 pi over 6. So that's how I find the angle, by finding multiples of those angles. Just increase one at a time. And I never even, if you give me a point, say, oh, this is the angle, what is this XY coordinate? I don't know. I don't memorize them, but instead I draw a right triangle using the x-axis and then try to use the special right triangles that you already memorized, the 30, 60, 90, and the 45, 45, 90. It's just that I memorized the hypotenuse and the legs in such a way that it's very helpful to me in the unit circle. So I'm going to leave it to you to decide what to do. Like I said, you don't need to memorize a unit circle, but you do have to know the special right triangles. You kind of know that already, I believe. You just probably memorize the values differently. But in this case, we always want to make sure the hypotenuse are 1. All right, any questions? So next class tomorrow is mostly going to be review. That's one thing that I'm still debating whether I should talk about it or not, but I think if I have time tomorrow, I just go over that. If we don't have time, then I'm going to leave it out. All right. On that note, so if you have any questions about the exam that's coming up, or when you are working on the homework currently, feel free to bring those questions to the class tomorrow. All right, 8:14, so I should have let you go 5 minutes ago, but anyway, I'm going to let you go now, and I'll see you tomorrow. Goodbye, everyone.
Thank you.
All right, take care. Thank you. Yep, thank you. Bye-bye.
Hey, can I ask you a question real quick?
Oh, yeah, go ahead.
So I was looking at the My Courses thing, and there's like 2 separate assignments for homework 5. One seems to be like totally blank, and the other one's the homework assignment. Is that like I'm not sure if that was like a mistake, or are you like if there's like an upload button I'm missing on the second assignment?
Yeah, that must be. So that's only one homework 5. I will go inside and delete the one that's blank. just if you have it open, just work on whichever that actually has the content.
All right, sweet.
I'm glad you brought it up. Thank you. I'll mention that tomorrow.
Yeah, no problem. See you tomorrow.
All right. Thanks, Brian. Bye-bye.